So we are going to start with subsets. What is a subset? We call a set A of set B if every element in set A is also in set B. The notation for subset is A sideways U of B that simply means A is a subset of B. Let's take an example. I'm going to pick A to be 1, 2, 3, 4, and B to be 1, 2, 3, 4, 5, ... all the way up to 10. If someone asked you, is A a subset of B? The answer is yes. Why? I can write B as 1, 2, 3, 4 over there. That's the set A. Oh, sorry. A. And I have the other numbers 5, 6, all the way up to 10. And if you look at it, the set A is part of the set B. So set A is within set B. So A is a subset of B. So A is just the set containing the element M corresponding to Monday, and B is all weekdays. Set A is part of set B. So the answer is yes. Set of natural numbers is the set of natural numbers part of the, set of even numbers part of the set of natural numbers. Well, we know what set of natural numbers is. 1, 2, 3, 4, 5, 6, 7, ... keeps on going. I can rewrite this as 2, 4, 6, 8. That would be the set of even numbers, and the remaining odd numbers I can just write it outside the set. And that is simply the set A. So A, 1, 3, 5, 7, ... A is a part of B, so the answer is yes. Going back to problem 2, one we just did, the set of natural numbers starts at 1, goes all the way up to whatever number. It does not contain 0. So A is not a part of B, so no, A is not a subset of B. Problem 4, is A subset of B? Well, I can rewrite A. If I simply look at unique elements, I have 1, 2, 3, 4, 6, 8, and 12. My question is A a subset of B? In other words, is A a part of B? Well, some of the elements in A can be found in B, but not every element in A can be found in B. I cannot write B to be A, comma, whatever other elements that I have. By all means, B has only 3 elements, 4, 8, and 12. So A is not a part of B. So the answer here is no. Okay, so in terms of notation, I would say A subset of B, but since it is not, I'm just going to cross through and say A is not a subset of B. Now, if one asks you, is B a subset of A? The answer is yes. The reason being, I can write A as 1, 2, 2, 3, 6, 4, 4, 8, 12. And we have repetitions. I don't want to get rid of the repeating elements because we have to keep the repeating elements also. It would be wrong for me to discard repetitions when we express sets in roster method. Inside the set A, I have the set B, and the other elements are just hanging out. So B is a part of the set A. So B is a subset of A. In our notation for subsets, I used that sideways U and I put a dash below it. Now, that would mean we are including equality also. So the subset implies there is a possibility. Oh, I should probably write this separately. So if we have A subset of B, here there is a possibility that A is equal to B. Naturally, if A is equal to B, then they are subsets of each other. A would be a subset of B and B would be a subset of A. And extending that idea, an important remark is every set is a subset of itself. In other words, now, in other words, A is a subset of A. According to our notation, for something to be a subset, we're saying that A has to be a part of B, or A could be equal to B. So this simply means, this notation means part of B or equal to B. And that is what we mean by subset of B. When we say A is a subset of B, I'm stating A is a part of B or equal to B. If that is true, then A has to be a subset of A because A is always equal to itself. Now, we have a special name. We call it a proper subset. Why do we call it a proper subset? Well, technically, if something is a subset of something, truly speaking, that something has to be a part of the other bigger entity. So for something to be a proper subset, for a set to be a proper subset, it strictly has to be a part of the other set. It cannot equal to the other set at any time. So if A is a part of B, which is also a set, but could never equal B, then A is a proper subset of B. So A, proper subset of B. And if you notice, I'm not using the line under the sideways U because there is no equality. A could never equal to B. So here are a few sets, and we want to know if A is a subset of B by definition, or is it a proper subset? The first one. A is 1, 2, 3, 4, 5. And B's got a bunch of elements. If I rewrite it though, I would have 6, 7, 8, and 1, 2, 3, 4, 5. But 1, 2, 3, 4, 5 is simply the set A. So we have 6, 7, 8, and the set A. A is a part of B, so A is a subset of B. Now, A could never equal B because according to our definition of equality, if two sets are equal, they must have the same elements. The order doesn't matter, repetition doesn't matter, but they must have the same elements. Set B has a bunch of extra elements, 6, 7, 8, respectively. So the first case, it is a proper subset. So A is the proper subset of B. Number 2, B is simply a different order, is in a different order than A, but they are equal. If I rewrite it, B is nothing but A. And we know every set is a subset of itself, and they are equal, so A is simply a subset of B, not proper. Last case is, it's an interesting case, trivial, but interesting. So A is an empty set. B, well, it is a set and every element in the set is a natural number that's neither positive nor negative. Well, the set of natural numbers start at 1, go all the way up to infinity. For a number to be neither positive nor negative, there is only one number, and that number is 0. And clearly 0 is not a natural number. So set B has to be empty. So both sets are empty. So A is equal to B. And we know every set is a subset of itself. So we will simply write it as A as a subset of B. Let's take a set or an empty set, call it A, and now I'm going to go for set B. 5, 12, and 39. Those are the numbers that are, or the elements that are in set B. What is an empty set by definition? Well, by definition, an empty set is any set that contains nothing, no elements whatsoever. Well, if that is the case, I could write the set B as a set that contains nothing, followed by 5, 12, and 39. Because nothing is part of B. So I can rewrite this as the empty set, comma 5, 12, 39. So the empty set happens to be a part of the set B. In general, it is a part of every single set. So the empty set is a subset of every set that you can think of. Not only that, the empty set is a proper subset of any set. The reason being, I cannot take a subset that is not empty, such as B here, containing 5, 12, and 39, and say that B is equal to the empty set. Not possible. The empty set can only be a part of another set if it has elements, unless we are talking about itself. So if I have an empty set, could it have an empty set in it? Sure, but then still it's empty. It would be meaningless to put an empty set within an empty set. So the empty set will be a subset, but it is always a proper subset because it will be a part of the set B. The equality is not going to hold because the moment you say equal, then we're talking about the same set, and that set is the empty set. Now we turn our attention to the number of subsets in a set, or number of subsets that you can form using a set. Well, let's consider the set that is empty. It is an empty set. What is the cardinality of an empty set? It is 0. How many elements does the set A have? None. So no elements at all. Well, we've already established that the empty set is a subset of itself. So A has one subset, and it is the empty set. So the empty set will always have one subset, and it is itself. Now I have a set that contains only one element. Let's say it has the number 1. I can rewrite this as the empty set, comma 1. A set that contains nothing, followed by 1. Well, if that is the case, then what are the subsets? One is a set that is part of, I'll call this A. The empty set is a part of the set A. So those are the two proper subsets we have. And the cardinality of A is 2. Going to consider a set that has 2 elements, let's say 1 and 2. Well, I can rewrite it as containing nothing, comma 1 and 2. And I can break this down. Well, I can break this down into subsets. Every set is a subset of itself. So I've got the first one, which is A itself. The empty set is part of the set because we've said empty set is a subset of every set. 1 is a set on its own. 2 is a set on its own. But this is the same as saying A. So I have 4 subset possibilities. So the number of elements of A in this case is 2. The number of subsets that I have, 4 subsets. Suppose we have a set A, and it's got 3 elements, 1, 2, instead of doing 1, 2, 3, let me do 1, 2, 7. I can rewrite this as the empty set, comma 1, 2, 7. The total number of elements in the set, distinct elements, would be 3. Now, I cannot count the empty set as an element because I'm inserting that in there using logic, because every set will have an empty set because nothingness is a part of something. So I cannot call the cardinality to be 4. It is actually 3. You cannot include the empty set. Now, what are the subsets? Well, we know A is a subset of itself. So the first possibility is A itself. The empty set is a subset of every set. So I'm just going to write that. 1 is a subset of A. 2, the set containing the element 2 is a subset. Set containing 7 is a subset. Set containing 1 and 2 is a subset. Set containing 1 and 7 is a subset. Set containing 2 and 7 is a subset. And that is all. Can't write anymore. Now, in total, I have 8 subsets. Starting with the first one, I have cardinality of A to be 0. I'm going to simply write that one subset A is supposed to have as 2 raised 0. Any number raised to the power of 0 is 1. Here in number 2, case number 2, I have 2 subsets. Oh, my bad. This is 1 element. I'm sorry. I don't know why I put 2 there. Now, the 2, I can write it as 2 raised 1 subsets, because 2 raised 1 is still 2. The next case, I have 4 subsets. I can write the 4 as 2 raised 2 subsets. 2 raised 2 is 4. I have 8 subsets. So 2 raised 4, oops, sorry, getting excited here. 2 raised 3 subsets. And so on. So the set containing 4 elements would have 16 subsets and so forth. So in general, a set containing n distinct elements will have 2 raised n subsets. N distinct elements will have 2 raised n minus 1 distinct proper subsets. This is very, very important, the distinct part. And I got rid of 1. So, for instance, what does it say? Well, I mean, what does it mean, the 2 statements? Well, I wrote the cases earlier, 0, 1, cardinality of 0, 1, 2, 3. Number of subsets is given by the formula 2 raised n. So 2 raised 0, 1, 2 raised 1, 2, 2 raised 2, 4, 2 raised 3, 8. Next case, 2 raised 4, 16, 2 raised 5, 32, and so on. But then I went to part B here, or remark B, and I took away 1 proper subset. And I'm saying there will be 2 raised n minus 1 distinct proper subsets. Is there a reason? The reason is that we want to get rid of the empty set because of the word distinct. If I have a set, say, set W with elements 5, 19 and 24. And I can write this, well, something containing an empty set. And 5, 9, 24, perfectly fine. But then I can also write it this way. Empty set, comma, empty set. Put them together, you still have an empty set. You're not going to get anything new. So I can keep on throwing as many empty sets as I want, but logically, no matter how many nothings you put together, at the end of the day, you have one big nothing. So the sets cannot be, the subsets will not be proper if you have the empty set, because for a subset to be proper, it cannot equal itself. But if you kept the empty set as a subset, it can equal itself, not just once, infinitely many times. So from a logical standpoint, if you're looking for distinct proper subsets, you will have 2 raised n minus 1. If you're simply looking for number of subsets, you would have 2 raised n. So 2 raised n proper subsets, distinct proper subsets would mean 2 raised n minus 1.